Hey, I'm back, guys. Been a little while. Thought I would kind of show you where I'm at on this. Kind of looks like a mess right now. Getting things put in here and starting to get some of the wiring hooked up. It just takes a little time. You just follow your schematic and it's not that difficult, really. There's a lot more wire that yet has to go in. Little resistor blocks. This one will actually sit down over here on top of this socket. I've got the other one already located and soldered in right here. And there was a couple, three of them that was out of tolerance, so I actually hid inside some resistors right inside here, so when it's actually sitting in there and all the other wires coming up through like this one does, they'll pretty much cover them up so they won't be seen. This has been restuffed with a new electrolytic cap. Didn't have a 50 volt. That's what it calls for, 20 microfarad at 50 volt, but I did have a 22 at 350 volts, so it's more than protected. Wanted to talk a little bit about these guys here and this here. Don't know if you can see them real well. They're flex resistors, although the insulation has gotten extremely rock hard on them, so that I've covered them up with heat shrink tubing. When you do have like insulation that's really hard and you need to move it, like to cover it up, and it's kind of hard to run your heat shrink around a curve, especially with some of the tight curves they had on them. You can actually heat that old insulation up. When it gets warm, good and hot, it will be real flexible and you can flex it back out. Now once it cools, it's hardened back up again, so you can get it straightened out, put your heat shrink tubing on it, heat shrink it down, and then keep it heated up and bend it back into position that you need it for. These had to curve around. This one hooks down in here. This one will hook down to a ground point down here. These both go to the filaments for biasing. Remember, the filaments on these tubes, some of these tubes are directly heated, so the filaments do make they are the cathodes. The other flex resistors that's in here don't have the rubber insulation on them. They are high wattage, a little bit higher wattage. They're probably about like a 1 or 2 watt. So they've got more of a cloth type material on them, more like your regular old style cloth insulation, but it's high temp. It can withstand some heat. But all these are nothing but resistors that they use throughout the radio as opposed to regular resistors. Now let's see what else. Basically it's just connecting up, getting stuff hooked up. I've gotten it, the power supply pretty much kind of in place. Still got to get the electrolytics hooked up. There's also 2 more up this direction. There are 4 electrolytics all together, not counting this other electrolytic. That's more on the as a bypass. The tuning condenser is in place. These are some of the wires. I got one wire hooked up. The rest of these get hooked up. So now I had a few things I wanted to kind of talk about. As far as well, like this can here and this one here and the others that's in here, these are not hard to take apart. I know there's been some videos on them. there's a plate on the back side, or on the bottom of these behind here. It's soldered into place, and a regular soldering iron is going to, it will give you a little bit of trouble trying to get it out. You might get a heat gun to work for you to unsolder them. Basically what I did was, what I use is just the this soldering iron here. It's 100 or 150 watt, but the main thing about them is they've got a real massive tip on them, so they don't cool down. And then I'll take and set the can up to the side and just start letting the solder flow down to one end. They're filled with wax, so that really helps you. The wax will start basically going to almost like a steam, the heat on there, and it kind of blows away what little bit of solder may be left that doesn't fully flow down. And I'll just keep moving it until I get down here just well, like on this one here, a little bit left. And then I'll get in there with a knife or something, X-Acto knife or something, just to get it started, lift it up, get a screwdriver underneath it, and it'll pop loose, and you can just take it right off. And then the rest of it is just unsolder the connections to the different points here and pull your capacitor out, clean it all out. There's not much in there. It's mostly the capacitor in there. Basically what's in there is this. This one's kind of nice because it's got the date, easily read date code on it of September 25th, 1932. They all have a date code, but a lot of them, the number, part number and stuff is actually stamped over top, so it's kind of hard to read it. But that's all that's in there. There's, let's see, yeah, 4 caps in this. That's all sandwiched together, wrapped up as one. This would be the ground. Anyway, you put your new caps in there, solder them back in, and re-rivet it back in place, and you're done with it. Now the big boys, these guys seem to be in good shape. They measured pretty well what they're supposed to measure according to the schematic, so I see no reason to take them out. It's kind of hard to hide other type resistors. These are kind of give you some idea what they are. They've got a lead cap on each end. It allows you to solder to, but it's a porcelain tube. It's got a very fine and very small hole in it, and that's where the carbon goes down through. It just looks like a pencil lead, a very small pencil lead that goes down through and is soldered at the ends into these lead caps that's on there. So that's what's in them. Being it's porcelain, there's not much you can do with it. On the other Atwater Kent, the 67C, I happened to have some tubes very close to the size that were large inside. They weren't porcelain, and I was able to actually fit the caps back on and put a resistor inside, but I don't have any more tubes of that size. A few more caps has got to go in. These guys here, they call them quality capacitors. They were pretty easy to do. They actually come out the end at these little eyelets, so I just heated them up. They're just actually just wax at each end. That was it, mostly a wax plug, and pulled them out and put the new ones in, hot glued them in, and they fit. One fits here, I believe the other one's on the other side, and they go from, this is the 2 output tubes, which you can't see. I'm pointing at a place here. These will go in here on each plates of each of the 2 output tubes to ground, and they're basically kind of help filter some more of the high-pitched sounds and allow more lower pitch to pass through and at least have more definition to it. They, like I said, Outward Kent calls them quality condensers. Now, speaking of the output tubes, I want to talk about, I had said something about it in an earlier video about what they call push-push. You have two output tubes working in conjunction, feeding the output transformer, which is here, which you may notice is potted. Everything was potted, pretty much other than the RF coils, chokes. And I want to talk about what push-push is. It's a term that's not used anymore. It was a term that was used back in the day. It was actually coined, I do believe, by RCA was the ones that actually coined it. Most push-pull amplification done back when this radio was built was Class A, and they did that. Well, actually, you can find 40s radios, even 50s radios that use Class A push-pull. The main reason was that, at least it started out as Class A, was they used triodes, and the old triodes that they were using to try to get them to work in any other type of class, especially in a push-pull environment, they just had a lot of troubles with distortion, had a lot of troubles trying to keep the bias steady. So the general sense is either run AB or run B as a push-pull. That's your better way of doing it. But these guys are actually running at B. Now these are tetrodes, meaning, you know, they're not a pento, they're not a triode, they're a tetrode. They have 4 elements. They have 2 grids. You have, which is standardized as being, well, normally you would see them as, you know, you'd have your cathode, control grid, screen grid, and then plate. But what they do with them, and these particular tubes especially, the number 46s, is they'll tie the screen and the control grid together in these outputs. And what that allows them to do is they can actually, to get it to operate in Class B, they only have to run it at 0 bias. Normally, any other type of tube to run at Class B, you have to bias it about halfway to cutoff range of your negative voltage. So say the tube cuts off at negative 10 volts, you would bias at negative 5 or even at negative 10 to get Class B to operate. Because you only want half the wave to go through. These guys, when we tie the grids together, actually allows us to do this at 0 bias. Now, if the negative going signal, in other words, when the signal coming into them is going negative on the sine wave, which will force the grids to go further negative, they literally just cut off. Nothing gets through. The tube does not pass no current, and nothing gets through. The tubes are shut down. When they go positive, which makes the grid positive, which normally is a no-no, but with the 2 grids tied together is perfectly okay. When the grid goes positive, then the signal can get through. But we end up carrying a lot of current. They start really drawing a heck of a lot of current when they do go positive, because the grid's drawing current, the plate's drawing a large amount of current. They click on really quick, and you get a real strong positive going signal, much stronger than if you operated them as Class A. So you can get wattages, pretty high. As a Class A, amplifier. They run about 1.25 watts. As Class B, they can run upwards of 20 watts as a Class B push-pull. So I've really drastically increased the wattage output by doing that. But they call it push-push. And the reason why is at the time, the idea of push-pull and the way the name actually came about was you had one tube pushing while the other tube was pulling, because one signal was going one direction, the other signal was just dead opposite of it, to get the tubes to operate, because what that was just the whole signal going in there, and you had to actually you had one tube going negative while the other tube's going positive. So the way these are operating is both are going same time, positive and positive, because they only pass the positive signal. So what they decided just to coin it as push-push, because instead of having the reverse where you're pushing and pulling, you're what appears to be pushing and pushing. But actually today's terminology is still push-pull. It's still called a Class B push-pull, because that's really all it is. It's nothing more than that. You still have to have a transformer for the grids and an output transformer specially designed for push-pull for the output. You've got to have your 3 different wires, your center tapped output transformer. You also have to have the secondary center tapped on the interstage transformer feeding the grids. So, but I wanted to kind of clarify what this is and how it works. The Type 46 tube, I believe, is the only one that RCA made that actually operated this way. They sold a lot of them. They are really, really good tube. The one nice thing about it, at the time especially, but was the fact that part of your signal that was going through your radio, the tubes were actually shut down. And if you had no signal going into the radio, not much sound at all, the tubes were shut down. So you wasn't drawing a lot of current. But when they did kick on, they would kick on hard and draw quite a bit of current, and that's the whole purpose of why you're using the 83 rectifiers, because they tend to regulate the voltage a lot better when you start drawing a heck of a lot of current real fast. So I wanted to kind of explain how that works, and if you want to see a close-up of the schematic, I'm going to rotate it to the screen here and kind of zoom in a little bit. So you still have, it looks like a standard arrangement, except you do have the 2 grids tied together here. Now they're using a 46 driver. In its case, they actually tied the screen to the plate, so basically it's running the same voltage as the plate, but it's operating in Class A operation just to feed the primary here. But you see we got a center tap secondary to actually adjust what's going on, but actually these 2 tubes will be, they only conduct when they go positive. But what's happening is this one's going positive, this one will be going negative at that time, so only this one's conducting and it feeds the signal in. In the next cycle, this one then will be the one feeding the signal in. Now it seems like something that you would consider as being, how can it put out a lot of wattage? Well, because it doesn't seem like they're operating truly fully, being that they're Class B, and doing that and shutting down on half the signal. But what you got to realize is these two, the change in signal from positive going to negative going is happening relatively fast, even at very low frequencies, say around 100 hertz or 40 hertz or 80 hertz. that's still 80 times a second. It's actually changing 160 times a second actually, and for 80 hertz. So it's not something your ear's going to hear, but each tube is allowed to really produce quite and run very hard when they do kick on. The grids draw a lot of current and feed the plate, and the plate current in there, and we'll feed back through the ground here, but we end up getting the tube going at its maximum amount. That's how we get our highest wattage out of it. So we can go from something with a Class A single tube of maximum 1 1/4 watts, around 1 watt or so, to a Class B designed this way with this particular tube to upwards of close to 20 watts, and really not draw much more current than a much lower wattage tubes overall. So now a few other things I want to discuss, and I'll probably hit real quick on here. This is taking longer than I thought. It was going to take this long. Something that I wanted to talk about, I have been meaning to talk about for a long time, and that is, let me zoom back out. You have your standard ICO 950B. It's a capacitor tester. All right, it's a capacitor resistance comparator bridge. You check for leakage with the eye tube. Runs up to around 500 volts, and you can check leakage. That's not the only thing you can do with it. Say you want to check some other leakage. Now, like me, I don't use it on everything, but like these rebuilt cans here. Now let me get this back down. I'll come down here. You probably can't see the resistor or the capacitor inside here, but this is rebuilt. I use the same stem, just cut it off the old capacitor that was in there, and just use the same stem, and brought up my lead and connected to it, and then, well, basically what I did is drilled a hole and put a screw in it and threaded it. Connected the positive lead, drilled a hole here, brought the negative lead out here. That way I can still use basically the connection point here, and everything looks pretty much the same like down here. Instead of like maybe run wires through or anything. It's generally how I do these cans. I try to make use of the same type of connection. Now what I did was, the old rubber in there was shot, so what I did was cleaned it out and just used several layers of heat shrink, and then the last little bit was just hot glue to lock her in, and then tightened down the nut, and that locked it in fully tight, and then put my the piece back on here that you soldered to. But even doing that, even with heat shrink and everything else, sometimes you're not absolutely sure if this is good. So what you can do is you can use the capacitor bridge and tie onto here, and of course you're actually just checking the capacitor that's in here. Well, it's a new capacitor, it should be okay, but you can feed it up. These are 450 volt, and I can feed it up to 450 volts and see if everything's fine. Now if it shows good, which means not only the capacitor is good, but it means, and what I'm doing is, when I do this test, I tighten this down and make sure the contact is to here, ground. So that also means that at least to 450, 500 volts, that insulation is holding up. And that's a nice thing you can do with one of those. The other thing is if for some reason you feel that the need to go beyond just an ohm meter of looking at, say, a transformer, whether it's a power transformer, output transformer, whatever, because not only should you check, you know, your windings and make sure, and that's one point I want to make, when you're checking transformers, whether they're IF transformers, output transformers, audio transformers, or whatever, power transformers, ohm scale. Use your ohm scale. Don't use continuity. Continuity is for checking wires, switches. That's really all it's for. As far as checking transformers, you want to use the ohm scale. That way it's accurate. It'll tell you basically what ohmage you got there. But the other thing you want to do is once you check the windings, you want to really check to the frame of the transformer for most transformers. Make sure you don't have an inner winding short to the core, which you could have. But what if it's not really a direct short? What if the insulation is just starting to break down, but it's not direct? It could only break down, especially on the high tension. These guys here, these are the heater filament windings. Okay, so they're, you know, one's like 6, well actually on this it's like about 2.3 volts or something like that, or 2.5 volts. The highest voltage is on the rectifiers, which is 5. But the high tension, in this case it's like 600 volts or 650 or something like that. And the other one's like 400. Remember, this has got 2 high tension leads on it. Those, at those voltages, somewhere in there could leak. There's a possibility. And that's where you could actually check those with the bridge and see if they're alright. They're not shorted or not leaking to the case, to the core, or anything like that. Same with output transformer and stuff of this nature. So you can check that stuff, you know. So basically that bridge is good for more things than just checking capacitors or looking at resistors and comparing and measuring values and so forth. Now the nice thing about it is I can apply, you know, upwards 500 volts, and if there's a dead short, all it's going to do, say there is a dead short, all it's going to do is just the eye is going to go open. Nothing's going to blow up because of the way the thing works. And I kind of drew a very rudimentary deal here of how it works. This is as simplified as it gets. When we're doing leakage, this will be basically how it's hooked up. And it's a Wheatstone bridge circuit. This is the capacitor, or at least this is where your leads are. Okay, this would be what you'd be connecting to check for leaks or shorts or anything, and generally you are plugging capacitors in there. But the rest of the bridge will be made up of resistors, the eye tube in the center. Now for the eye tube, well, I said wrong, the eye tube would stay closed if it's dead short. For the eye tube to be, if there's a dead short and it's closed, what makes it go closed is this side and this side is balanced. In other words, the same amount of currents flowing through here is flowing through here. When those two are balanced, the eye tube's closed. Nothing's going through here. If, say, the capacitor, or you have no short or nothing, there's no leakage here, that opens this circuit. And what that does is change how the circuit's operating, so the eye tube then opens up, because now we have an imbalance on the 2 legs coming around this way. All the current's trying to flow this way, although some will go through this way, which is the way it's hooked up, and flow through the eye tube and cause it to open. But if there is a dead short here, not only do you still have this resistor, but even if that wasn't there, you still got this side that's going to keep and protect the circuitry, the power supply circuitry in here, from being overloaded. Everything's sized out so that it can handle what loads on this branch. So I just wanted to show that, but also tell you that there is other usages for it. You can even check a piece of wire if you really wanted to. If you were suspicious of it, you know, connect one of the leads on one end of it and connect anywhere along the insulation path with the other lead, and check it and see what happens. So if the eye remains open, the insulation's good. So anyway, this is really long, and I'm sorry about that, and it's going to take forever for it to upload. That's basically where I'm at. I'll continue on plugging away with this thing and connecting up, getting everything connected up, and as I move along I'll probably show another video. Definitely doing our video part way through again before we're actually to the point of flipping it over and starting to do our power up test and checking things. So until the next time, I want to thank my new subscribers. I'm going to make a video sometime this week. I'm not sure what day, but it's going to be basically to answer and to reply to a lot of the comments. I just have not had a chance to really get on there, so I apologize for that, but I do thank you for your comments. I do read them. And so anyway, thanks for your comments, thanks for watching, and thanks for subscribing and hanging in there with me. So I'll see you guys in the next video. You all have a good evening. It's evening here at this time when this is being recorded. So see you on the next video.